This is third video about hybridization. So in this video I'm going to explain hybridization in ethylene molecule, ethylene double bond containing molecule, and acetylene triple bond containing molecule. Let's see how we can explain hybridization in ethylene and acetylene. So this is ethylene, or another name is ethene. There's a double bond between carbon and carbon and 4 single bonded hydrogens. Let's talk about one carbon atom first. You can see the atomic environment around the one carbon. So single bonded hydrogens and another connection to the adjacent carbon. There are 3 bonds. So let's pick one carbon and write the electron configuration 1s2, 2s2, 2p2. So valency shell for the carbon is 2s2, 2p2. So let's write the orbital diagram for the valency shell of the carbon. 1, 2, 3. So in 2s2, 2 electrons, and 2p2 level there are 2 single electrons. This is 2s, 2p valency shell of the carbon. Same like we did before, let's do a promotion step, or we increase the energy one of the 2s electron promoted to the next highest 2p level, and then 1 electron remaining in the 2s, and in the 2p there are 3 electrons, 1 in each orbital. So it looks like this. Now there are 3 bonds around one carbon. 3 bonds means we need to make 3 hybridized orbitals. So how we can make 3 hybridized orbitals? We need 1s and 2p. So let's mix 1s and only 2p orbitals together to mix hybridized orbitals. Then the configuration is the hybridization is 1s and 2p sp2 hybridization, sp2. So 3 orbitals mix to form 3 sp2 hybridized orbitals. In each orbital is having 1 electron. These are sp2 orbitals, and the remaining 2p orbitals, 2p atomic orbital is here. So these are hybridized orbitals by mixing 1s and 2p's, and the remaining unhybridized atomic orbital is 2p here. Now you all know p orbital is dumbbell shaped. The resulted sp2 orbital, one lobe is large, the other side lobe is small. The same thing is going on for the second carbon, because both carbons atomic arrangement same. Second carbon also the configuration same. First we write the orbital diagram, and then we promote 1 electron to the next highest level, and then we mix the required number of orbitals. We need to make 3 bonds, then we need 3 hybridized orbitals. To get 3 hybridized orbitals, we need to mix 3 orbitals. So s, and when we need 2 of p's, overall 3, we make 3. Now on each carbon, let's see how the arrangement looks like. Let's pick one carbon. There are 3 hybridized orbitals. So one hybridized orbitals place like this, another one we can place like this, and another hybridized orbitals. This is how hybridized orbitals on one carbon. So these are sp2 hybridized. So sp2 hybridized orbital, 2 orbitals overlap with hydrogen's 1s orbitals to make CH bonds. So these are the sp2 of the carbon, and this is sp2 of the carbon, overlap with hydrogen's 1s orbitals to make CH bonds. These are hydrogen's 1s. And the remaining hybridized orbital on this carbon is overlap with another hybridized orbitals on the next carbon. Right? The same pattern here. Make CH bonds overlapping with sp2 hybridized orbitals on the next carbon with hydrogen 1s, and this is hydrogen 1s and sp2. Right. Now what happened to the remaining 2 p orbitals? Now this you can see sp of the first carbon hybridized orbital overlap with sp2 hybridized orbital. They are along the internuclear axis. We call this is internuclear axis. So along the internuclear axis, they overlap. The hybridized orbital sp2 overlap with another carbon's sp2 hybridized orbitals. So these kind of orbital overlap along the internuclear axis, we gave a name as a sigma orbital. This is Greek letter sigma, sigma bond. Now let's go and talk about the remaining p orbitals. We use all sp2 hybridized orbitals on each carbon. Now each carbon there is additional unhybridized p orbital dumbbell shape is there, like this. So these unhybridized p orbitals overlap only partially from above the plane and below the plane of the molecule. So this is internuclear axis. I draw in the dashed line. So these orbitals overlap above the plane and below the plane only partially. So that is forming pi bonds. So I will draw the overlap separately here. 1 p orbital, 2 p orbital in one carbon overlap with another 2 p orbitals only side by side. Only the above the plane and below the plane. It's only partial overlap. So this result a pi bond. So in a double bond, if we draw a double bond, CC double bond, so one is sigma, the other one is pi. Right? One bond is sigma, the hybridized orbitals overlap along the internuclear axis like this, and the other one is pi bond. It overlaps unhybridized atomic orbitals only above the plane and below the plane. This is how the structure looks like. The same way we can discuss acetylene molecule hybridization. Let's see what is acetylene. Acetylene is CC triple bond. In between carbon and carbon there is a triple bond and then one hydrogen attached to each carbon. So let's try, let's pick one carbon and then draw electron configuration, carbon electron configuration 1s2, 2s2, 2p2. Valency shell is N is equal to shell. So let's draw orbital diagram of the valency shell. Now next step is electron promotion. Let's promote electron, one of the 2s electron to the 2p. This is 2p and the 2s after promotion step. Now we need to make only 2 bonds in each carbon. This is one side connection, and to this carbon this is another side connection. Only 2 connections. So let's make let's mix only 2 atomic orbitals, 1s and 1p, to make 2 sp hybridized orbitals. So each sp hybridized orbitals having one single electron. So what happened to the remaining 2p orbitals? The remaining 2p unhybridized orbitals still there. This is after hybridization. So 2 orbitals mixed to make 2 sp hybridized orbitals. Why we need 2? Because each carbon is having 2 connections. Now let's see how these hybridized orbitals and dumbbell shaped p orbitals arrange on acetylene molecule. Carbon, there are 2 sp hybridized orbitals. So those sp hybridized orbitals, one orbital overlap with hydrogen 1s orbital to make CH bond. The other one overlap along the internuclear axis. This is the second carbon's sp hybridized orbitals, and that carbon, another sp hybridized orbital, make H bond. So these are hydrogen 1s, and these are sp of this carbon and another carbon, this same carbon sp, and the second carbon 2 sp orbitals like this. Now this is again the same like previously I explained. Along the internuclear axis, these two carbons sp hybridize, so it makes sigma bond. Now let's see what happened to these remaining 2p orbitals. The remaining 2p orbitals are on the each carbon one on one like this. The other one, let's draw a parallel along the z-axis and along the y-axis like this. So these p orbitals, dumbbell shaped p orbitals, are sideway overlap, and these two we draw in green. These two overlap sideways. So by overlapping these p orbitals side by side, above the plane and below the plane, like this, so they make two pi bonds. So px, py, and pc, they overlap partially above the plane and below the plane and above the plane. They make pi bonds, two pi bonds. Therefore, in acetylene molecule, now you can clearly see one sigma bond. The reason is sp hybridized orbitals overlap along the internuclear axis, make one sigma bond, and two p orbitals py and pc partially overlap to make pi bonds, two pi bonds. So triple bond is made by two pi bonds and one sigma bond. Right. I hope you will understand now what is the hybridization, how we can explain hybridization on acetylene, double bond containing molecules and the triple bond containing molecules. And also sigma bonds always resulted along the internuclear axis overlap, and pi bonds result by atomic orbitals, not hybridized, atomic orbitals overlap by sideways above the plane and below the plane. In a double bond, 1 sigma, 1 pi. In a triple bond, 1 sigma, 2 pi bonds. Thanks for watching.